We had begun looking at hashing. We had looked at how to hash using SHA-256. And then we did a hash on an additive group, where you take your data, your arbitrary data, and then you hash it to an element of a group, an additive group. So for instance, if you have Z3, I'm just using Z3, but we need N to be larger, N should be larger. So suppose N3 has, Z3 has 0, 1, 2. So you can take your arbitrary text, the whole of it, and then you map it to one of these elements randomly. That's what we call hashing to an additive group. So today I want us to look at how do we hash to a multiplicative group. Suppose you have elements of a multiplicative group, and then you have text. You have your data, and you want to hash it to that, or map it to one of the elements. How do we do that? And I've written here the steps. Of course, we know what elements of this additive group, multiplicative group are. For instance, when we talk of Z star 8, but let me talk, normally our N will be prime. If N is prime, it becomes easier than when N is not prime. So supposing N is 7, Z star 7, this set comprising of elements which are relatively prime to 7, 1, 2, all of them up to 7, are now up to 6. They're relatively prime to 7 and smaller than 7. Now, so if you have a text, you have some text, let me say a text like today was impeachment date, today was impeachment, something like that. And you want the whole of this text to convert it to one of these numbers. That's what we call hashing to a multiplicative group. So you want the whole of this text, however much big it is, you want to convert it to one of the numbers here and store it. After converting to a number, you store it as that number. You don't store the original text for security reasons. You don't want people to, supposing your enemies were to go through your laptop or so on, you don't want them to get your original text. So you then hash it to group and then store what you get. Now, so what I've given here are the steps that we'll be following to hash. So to hash to a multiplicative group, the first step is that we do the normal hash. You can use SHA-256, the normal hash. And we talked about this last time. When you hash using SHA-256, the text that supposing you had a long text, that text when you hash it, it's converted to hexadecimal number. Hexadecimal number. And this hexadecimal number is 64 digits. So converts to a 64-digit hexadecimal number. That's the first thing you do. You hash using SHA-256, and we had looked at that and also came up with a code to do that. So that SHA-256 would convert your data to hexadecimal number. Now that hexadecimal number, you then convert it to a decimal number or denary number. And then after converting to that denary number, you reduce that number. Of course, that number will be big, and you want it to be mapped to as an element of the group. So supposing your group is Z13, you had your text. Let me say this text is the one I want to hash. So this text, I would use SHA-256. SHA-256 gives me a hexadecimal number. This hexadecimal number, you convert it to decimal number or denary. After converting to denary, you reduce it mod 13. When you reduce it mod 13, what you then obtain is an element of this group. You obtain an element of this group. Okay. So if you reduce it mod 13, you'll get an element of this group, but we don't want 0 to be part of that, because 0 is a part of that. 0 is part of that this group. So when you reduce it mod 13, the best way is to reduce it mod 13 minus 1, which is mod 12. Not mod 13. Because when you reduce it mod 13, what you'll get are elements. You'll get 0, 1, 2, 3, all the way up to 12. So 0 is part of these elements. In other words, you're getting 12 elements. So the best way, I've said, we reduce it mod p minus 1. So in that case, 12. Then the answer that we get, we'll add 1 to it. We'll add 1 to it. So when you add 1 to it, you want to ensure that you have how many elements? 1 up to 12. You have 1 up to 12 elements. Those are 12 elements. Because when you do it mod 12, you'll get 11 elements. So you just add 1, then you have 12. You have 12 elements. So that is the easiest way of hashing to a multiplicative group. So the first thing that we did was just to use the normal hash. You can use SHA-256 or SHA, any other series of hash of SHA-2. And then after that, what you get is a hexadecimal number. That hexadecimal number, the next thing you do, you you convert to decimal. Then after converting to decimal, you reduce mod p minus 1. Then after that, add 1 to the result. Now, you can do it manually, but it will be tedious. It will be tedious doing it manually, but if you have a smaller text, you can try manually, hash it, and then after hashing, the number that you get, of course, you're getting a 64 digits. So converting 64 digit to a decimal number, of course, it will be easier again using a code. So you can do it using a code, convert to decimal, then this decimal reduce, again use Rust code, reduce mod p minus 1. But what we want is to combine all those steps in one code. All those steps in one code. And so it's the code that I want to share. So the following Rust code shows how to hash an input from multiplicative group mod prime number. So the first thing is that we get the hashed value by using SHA-256. You use SHA-256, you get a hashed value. This hashed value, of course, we will first of all convert to decimal. Then after converting to decimal, we would then reduce it mod p minus 1. So I've just explained what we are going to do. So all these components must then be in that code to do that. And that's why I've included them here. Now, I've said that the prime number although in my examples I've been using prime number 13, but I've noted here that the prime number to be used must be large enough to avoid collisions. We have talked of collisions. Collision is where, for instance, you hash. It's when you hash a value, you're supposed to get one one result. So collision is where you have two different, let me say you're hashing A and you're hashing B. And supposing you're hashing A and B, and then you get one hash. This is what we call collision. Because these are two different things, you're supposed to get two different results. So when you hash very small, when your P is small, for instance, P is 3, for instance, you see you only have two elements. I'm just using this as an example. If you take P to be smaller, let me say 3, and you have a text, there's a possibility that this word prime could be mapped here, and the word number could be mapped here. And if I was to continue mapping other words, for instance, this there, you may find that this there could also be mapped to this. And maybe this word used maybe could also be mapped to this, because we have very small options. You have very small options to map to. So there's a possibility that we might have several different objects, several different objects being mapped to the same image. There's that possibility. So, but when you use your P to be a huge number, so you have various numbers to map to, numbers to map to. So when you do that, the possibility of collisions is reduced. So you reduce that possibility of collision. I think that point, that's what that point means. I think it's clear. So we are using large prime to reduce on collisions so that we don't have, you see when collisions are there, even somebody trying to hack, somebody trying to attack our system may even get the correct result by just an accident. By just accident, because we are using a very small P. So by accident, by guesswork, this person can easily get what our original text was. That's what we want to avoid. Now, so the code that I'm using, I've added this create SHA-2. So this one, these are the libraries. So SHA-2 comes in. This is what will assist us in terms of SHA-256 also. Of course, we also have SHA-256. We have the number big integer to assist us deal with those big integers, and also we have this for assisting us get things like GCD and so on. And that is if you require them. Now, then we have we have two functions here. I have this function, SHA to multiplicative group, hash to multiplicative group. And then we have the input, and then U8. Then we have prime number. So this is the prime number you are going to use. For instance, if you are using 13, or of course it must be a bigger prime number. And then we have this hasher 256. So this is the part that is going to do the ordinary hashing using SHA-256. You can see it's immutable, meaning that it will be changing from time to time, so it's not static. Then we have the hasher update. Then we have let hash result finalize. So this is where now we read the final result for the hashing. After hashing the final result, then we convert that hash to binary number at this point. This we can see let hash hex. So this stands for hexadecimal. So this is a part that will be converting that to a decimal number. Now, in some cases, when that hash, if it's wrong, then it will not be possible to convert it to an integer. If there is any mistake, then this is the base, the decimal number. No, the base for hexadecimal number. So hexadecimal number, the base is 16. So you are converting a number base 16, an integer base, no, a number base 16 to base 10. So that is where we are doing it. Now, this part is to reduce that integer to an element of the group, and you can see it's the remainder. So you're taking what you get here, that integer that you get. Let me say, suppose you get a very long integer there. You reduce it mod p. So that this means the remainder is what so this number divided by that, the remainder is what is here. And this remainder is an element of the group, is a member of that group. Now, but I've included these notes, I've included the notes on what is happening at every step. I've included the notes at the, at the end of this code. You have the main function. The main function, this is the input. This is what I want to hash. So I've said I want to hash hello multiplicative group. Hello multiplicative group. Then there's this exclamation mark. If you remove any of this, if you remove this, the hash changes. Now, then I define my prime number. It has to be a bigger number, as we've already said, to avoid collisions. So this is my prime number that I want to use. So I want to convert this text to any member of the group mod this number. Any member of the group mod that number. So let me share the code, then we discuss what each of the parts will be performing, which role each of the parts will be performing. Now, this is the code. It's a very short code, it's not long. Of course, what is making it long is just those notes, the notes that I've included. So my P is here. And this is what I want to hash. I want to convert it to a number of the group. So if I run, what I get should be a member of that group. So it has given me this. This is now what I store. This is what I store now. Now we can reduce this to a smaller prime number for us to understand. Let's use 7, for instance, and convert this to group mod 7. Multiplicative group mod 7. So we expect to map it to any member of the group, an element that is relatively prime to 7. That's what we expect to map to. So you can see it has mapped the whole of that text to 4. It has mapped it to 4. But now the problem is 7 is a very small number. So if you try to reduce this, is if we reduce this text, we expect it to give us a different hash. But now, since we are only dealing with very few numbers, we may expect some collisions at some point. But let's see. I've removed the apostrophe. So doing that, the remaining text is mapped. You can see it's still mapped to 4. So this is a collision because those are different texts. Let me remove all. Let me remove all and run it. So when you remove all, it has been mapped to 6. But you can see what you're saying is when you use a very small p, there are chances of collision. There are chances that different texts will be mapped to the same number, which is not supposed to happen. You're supposed to have different texts mapped differently. So we can try another prime number, slightly bigger. Which one is that? So you can even try just 17. Let me try 17, or even 27 is slightly bigger. So 27 is not prime, but 29 is prime. So it has been mapped to 24. So let me remove this apostrophe and see whether it's mapped to the same thing. Should give us a different hash. This one is mapped to 10. So you can see there are several choices for this. Let me remove all. And we expect a different, although 17 is still, 27 is still, not 29 is still a very small prime number. We expect also collisions at some point. But that is how we do it. That's how we hash to. I mean, you can see we are just hashing to elements that are relatively prime to that. Those are elements of the group. Now, so that one becomes very secure. It becomes very secure because it's not, if you use a very big number, it becomes secure because nobody can really try to guess what number you did. And this is happening randomly. But as it happens randomly, there's consistency. The same word will be mapped to the same number. You cannot have the same word mapped differently. The same word will always be mapped to the same number. So that consistency is there. So that is what we do normally. You want to send somebody that text, and you send that person the hash. So when this person verifies that the hash that you send, and then also hashes the text, you send the text and then the hash. So this person receives this too. And this person wants to be sure that this message is from you. So if you want to be sure the message is from you, what it does now, it takes your message and then finds its hash. If the hash the person obtains is the same as the one you send, then it means the text he has obtained came from you. Otherwise, if there's a slight variation, then this person is sure that the message he has received was tampered with by somebody along the way. Now, so at this point, I'm just explaining what each of these parts is doing. I'm saying that SHA-2 provides access to SHA-256 hash function. So that is why SHA-2 is there, to provide that access, because SHA-256 is just in the family of SHA-2. So it's SHA-2 that gives us that access to SHA-256 hash function. Then the number big integer will be, as I said, will be used to handle arbitrary large integers because we'll be dealing with the larger prime numbers. And then this one, as I said, to assist us again in passing strings into large integers. And of course, normally it works very well for GCDs, but for this case, we don't have GCD. So its role will be just for passing strings into large integers. So we have strings, of course. If you are string and you're converting that string to a large integer, so that is the role it will be playing. Then hex, this is used to convert the hash. Remember the hash, when you use SHA-256, that hash will be hexadecimal. So that is why the hex comes in, to convert that hash into hexadecimal string. Also, what you get is an integer. Is a number. So we want it to be a string. So you're converting a hexadecimal number to a hexadecimal string. That is why the hash, the hex, that's the role of that hex. Now the main function, we had said it has, we have where you're inputting, and that is what the text that you want to hash, and the integer, the prime, the prime number that you want to use for the group.
There's a question that has been raised. Eugene is asking, how do you get these big primes?
Oh, okay. I was not seeing the chat. The prime numbers, we had, when we began with the codes for the code that can give us a prime number, the codes that can tell us if a number is composite, and so on. Of course, a prime number is that which has no common factor, which has no prime number that can divide it. A divisor which has no divisor. That's what the word I was looking for. So the only divisor is the number itself. But we have Rust code that can generate for us these prime numbers. You just tell it the range you want it to. We had done that earlier. Maybe I'll share that code again. So just give it the range. You tell it I want the prime numbers between this range and this range. Then it will generate for you the prime numbers. Of course, we have even superior libraries that can give us even very huge prime numbers. But I'll share that one here. So those prime, you just tell it, for instance, I want prime numbers between 2000 and 3000. Then it gives you all the prime numbers within that that category, that between that range. Now, so I'll share that. I'll show you the code and how it works for the prime numbers. So this is where we input. So you input what you want. Then there's also prime number. You input the prime number here. Then we have a point, the need for hash to multiplicative group. So this one is just called. It's called, and when it's called with the input and the prime number, it prints what you want. So this is what I'm referring to. So it calls for hash to multiplicative group. So where is hash to multiplicative group? Hash to multiplicative group was above. So the main function is calling for that. So you see what happened is this. You input this text, then you input the prime number, when you run, when you say cargo run, the main function calls for this function to perform its role. It calls for that. Where's that function? Hash to multiplicative group is here. So this is the function that the main function is calling on. So it's telling this function, can you now perform your role? And once this one is called upon, it begins performing its role. It begins from here. Begins from here, going down, performing its roles. So that is what is happening here. So it's just the main function has been asked. You have told cargo run. When you tell it cargo run, since it has the text that we want to hash, and it has the prime number, and it doesn't know how to compute, how to hash, it calls on the function responsible for that. It calls for that function. So that the function responsible does that. Once it has done, the main function takes over again and then prints, takes over and then prints the result. So that is what the main function is doing. The main function has only 3 roles. The first role is the input part. The second role is to call on this function. And once this function has done its role, the third role the main function does is now to print the result from above. So it prints, it just picks from above and prints that result. Now, I had explained these other parts in details. If you go above, I'll explain this. So you have seen these other parts, I've explained them in details. For instance, what this part does. The SHA-256 hasher. So this one creates the SHA-256 object that will be used to hash. So you see, you input, after you input, what you input is, of course, that's what we call the object. But now, after you input that object, then again, SHA-256 will produce another object. And this other object is the one we are talking about here, creates SHA-256 object that will be used to hash the input. And then we have this part, hash the input data. Now, so when you input the text, this text comes as a string, comes in as a string, but it has to be converted to what the code will be able to read. So this is the function that this part is playing. Hash the input data. So you're just converting it to what the program will be able to read. Then we have the finalize the hash. So this is after the input has been processed, finalize the hash, computes the final hash digest. We said the word digest means the output. So the hash, the output is what we call the digest. Okay, so you go through this notes. Of course, this is the last bit. We had already talked about it, that we're reducing it mod p-1. And I've said this ensures the result fits into the valid range, which excludes 0. So when you take the hash and then divide it by the prime number, this, what you write here is the result of the remainder. This is the result of the remainder. This sign means the remainder after division. That's what that sign means. the remainder after division. So when you divide, for instance, 7 by 3, what you write is 2, the remainder. So let me try and see if I can get the code for the prime numbers.
I was just asking, I was also curious. Hii SHA-256 inakwanga tu niko na swali.
Yes,
Hii
yes.
SHA-256 inakwanga na nini? Is it just and or gates? A series of, ama kuna operation nyingine bitwise inafanyika? Ni bit operation peke yake?
Kuna mahali umepotea kidogo.
Inakwanga tu a series of bit operations.
Yes.
Bit operations peke yake, hakunanga vitu zingine.
Now, ukitaka vitu zingine, sometimes you combine it with other things. For instance, in this case, you may combine in groups. Sometimes haikuji peke yake. So you may want to combine it with other things. But ikiwa tu peke yake. Yes.
Inakwanga tu and and or gates peke yake.
Yes.
Asa. Nilikuwa nimeona umesema uli implement hiyo SHA-256 ama ni?
Yes.
Nilikuwa nimeisoma mahali kuna mtu alikuwa anajaribu kutengeneza moja yenye unaweza verify. Alikuwa anaongea kuhusu venye it's just atajaribu kufanya na vitu zingine hapo.
Yeah, normally it doesn't work on just alone. If you want it to be more secure, kuna vile you may want to add in a few things here and there. But ikiwa kivyake tu, it will just convert to hexadecimal. And then you achia hapo.
Na niaje ni bit and or operations alafu inakuwa hexadecimal the final output?
Kuna vile yes.
Niaje inakuwa and or operations, bit operations peke yake, alafu the final output is hexadecimal. Hello?
Yes, nakupata. I'm trying to figure out the reason. Na reason siipati rahisi. Unexpect ikiwa na and or generate nini peke yake?
Bado output ikuwe bit, ikuwe binary bado.
Sasa there's a way hizo binaries zimekuwa converted to nini? Zimekuwa converted to hexadecimal. There's a way zimekuwa converted. Because what you get is a binary number. So if you have a binary number, there's a way you convert those binary numbers to hexadecimal.
Okay.
Just converting the binary number to hexadecimal. Wacha nijaribu find out SHA-256. Yeah. But let me first of all share the SHA-256. You look what is there. Before I share the prime, because it's on nimeiona haraka.
Alafu pia nitajaribu kushare. Nilikuwa nimefanya hiyo hashing to field. in Rust, lakini nilikuwa natumia Acox. Sasa ili nifanyia hesabu mingi hapo. Hadi ndo nimeelewa ni ilikuwa inafanya.
Ulikuwa mahash tu?
Ilikuwa na hash to field to hii scalar field ya hii curve ya BN12 381 hiyo curve, alafu nikaihash to field sasa elliptic curve. Nikisha kuwa na hiyo namba na naimap tu kwa nini nikitumia generator na map kwa field.
Okay.
Sasa hata sio mimi nilifanya hiyo hesabu, ilikuwa imefanywa na Aquax. Sasa walifanya hesabu mingi hapo, walikuwa na the tools.
Na the SHA-256 ndio hii hapa. So you can see, you can hear me?
Mwalimu, maybe naweza jaribu kusaidia kuansa.
Mmenisikia?
Hello, Kanani.
Sio chanue.
Okay, mi naona like okay, the reason as to why SHA-256 inatoa output in terms of hexadecimal, kama ni binary, tuseme uko na given number of bits, in terms of representation of numbers, uko limited to up to a certain number which you can represent. So tukiingia now as to why, unajua sasa why we are using SHA-256 ni kupata a very large number. So if we choose to represent it in terms of binary na tuko na a given bit machine, we are limited. So we need to go to another form of representation. So the hexadecimal part is now for displaying that huge number which cannot be achieved in binary. Because in binary you need to have more bits which we are limited.
Oh, so iko limited.
Yeah, like if you have a 2-bit machine, there's there's an upper limit to a number. Let's say to work with small numbers, if you have a 2-bit machine, you can only represent up to 4. If you have a 3-bit machine, you can only represent up to 8. But what if you have a result which is larger than 8? So you need another number system to help you in the representation.
Mm-hmm.
So that is where now the hexadecimal, why SHA-256 give out the output as a hexadecimal, ni like after pass maybe a text through SHA-256 algorithm, the output is a very large number which cannot be represented in binary because we have limited number of bits. So we now use the hexadecimal for representation. Yeah, that's my opinion, yani. But like sasa kama ni hivyo venye umesema unashanga mbona kama ni AND gates, why is the output an hexadecimal? No, the output ni binary, but like itakuwa limited, so we have to go to another, sijui nitumie domain, but domain is not the right term, but we have to look another way of representing it. That's what I think.
Kusave on space, yani hiyo the final output unaweza kurepresent nini, hadi nikaa nimeona hiyo stuff hadi
like you can be able to represent a large number in now that hexadecimal.
Okay. Yeah, what he is saying is okay. because it's giving us a reason why it is represented as hexadecimal. Of course, it will be easier, it will be readable, easier to read that. What I was struggling to think was how it converts that to, that's how I was getting to understand the question. And he has also explained the other way, which is okay. For me, I was looking at what I was, how I was understanding the question was, why is it giving this and not this? That is how I, but what he has given is why it's giving the other one, which is okay.
If you, Mwalimu, you can add on if you have done some research on how it is able to do that.
How it's able to do that? Hello?
Yes. Because me have answered why.
Yeah, that is what I was. Yes, the why is what was, because for me, what I normally think, it's just automatic, that's the default output. That was just the default output of SHA-256, but I don't know what normally happens. But I thought it was just default. I had never thought of if there is a computation that makes it possible. So the Y bit is what I was struggling to think why that. I've always imagined it's just a default. You give it this, then the result will be that. And the reason is what he has given, because hexadecimal will be easily readable and so on. The limitations of the binary. But the Y bit, that one, maybe we go and think about it. Now, I was sharing something, I don't know whether it's, I cannot see it from my end. I'm trying to see where I was sharing, maybe I unshare and then share. Okay, in fact, what I was sharing is SHA-256, and I was trying to look at it to see where the conversion happens. And I thought it was default, by default, that it will give hexadecimal. But then we need to go and think, how does it become by default? Now, so if you change any of these things, we expect that the hash here has to change. When you change anything, the hash is supposed to change. Okay, that is the SHA-256. I was also to share the prime, the one that will be printing for me prime numbers within a given range. I don't know how I named it. Let me try to share this one and see whether it's the one. Just a minute. I don't know whether it's this one. Yes, I think it's this one. Where you tell it where you want it to begin For example, let me say I want prime numbers between 300. Let me say 400. So you give it the range, just using smaller numbers so that we can have it run very fast and give us the results. So you give it the range that you want prime numbers between this range, and you can see it as told as prime numbers between 300 and 400 are the following. Then it lists for you those prime numbers. You may want to choose one bigger one out of that. And if you want them bigger, I'm adding 2 zeros. Let me see. Added 2 zeros. Let's see if we can get those prime numbers. Let me say, reduce a bit. Reduce and put a 9, another 9, so that there are fewer. That gives prime numbers in that range. So if you have a code that can give you very big prime numbers, then this is how you do it. You come up with a code, and that code is able to give you the prime numbers, the bigger, the length you want. For mine is limited because if I was to give it very huge numbers, then it may take longer, or that it will still print, but it might take long. It can even take a whole week. You can see it has given us all prime numbers in that range. All prime numbers in that range. So that's how you can tell bigger prime numbers if you want to use them for hashing. But of course, sometimes the numbers we use, it's easier to use the hexadecimal numbers. Hexadecimal numbers, it's easier to use those hexadecimal numbers, especially in the normal real life situation where we are doing hashing. The numbers that are commonly used in most cases will be those hexadecimal numbers, not these decimal numbers. Okay. Any other question or something we can go and research on and find out how it happens? Okay, I think we can then end our class at that.